All right, this is a pretty complicated question. It asks you to take all three different cubic unit cell structures, and it asks you to derive an equation that relates the length of the unit cell to the radius. And so it actually wants to know the radius of the atom equals in what terms of the length. So we're going to assume that we understand what these structures are. In other words, how the atoms in the unit cells are arranged. In a simple cubic unit cell, I've got atoms at each of the corners. Now, I'm only going to show two of the atoms because these are the important ones. But what I want to do is I want to make sure that we understand the important point of this drawing. When you do these kinds of examinations of the unit cells, it is important to know which of the atoms actually are touching each other. In a simple cubic unit cell, all of the atoms are at the corners of the cube and they all touch each other. Okay, so they're all, each one touches each other. And so the two atoms touch each other along the edge of the unit cell. Let's take a look at the face-centered unit cell. So in a face-centered unit cell, I still have four atoms around the corners, but I've also got one atom in each face of the cube. Again, it's important to know which of the atoms are touching. And so what we find out with this, now I know they're not perfect spheres. Let's just go ahead and ignore my drawing. This is the best I could do. It's pretty good considering it's not on a chalkboard. But at the end of the day, in face-centered cubic unit cells, it's the diagonals that touch. So one corner through the face, the atom at the face, touches the other atom at the other corner. Now, what about body-centered cubic unit cells? Now, body-centered cubic units, say, hold on a second. I wanted to come back here. I'm going to show you the diagonal through the face is where the atoms are touching. Okay. And so this is the triangle that I'm going to consider later on in the game. What's next? All right, so now we've got body-centered cubic unit cells. So I've got, in body-centered cubic unit cells, I've still got all four atoms around the corners, and I've got one atom that sits in the middle of the cube. And so that's this atom there in the middle of the cube. So what I've shown is the two atoms on the corners, but they're at diagonals. They're not only diagonals along a face, but they're diagonal through the body of the cube. So what are the atoms that are touching in this case? They're the atoms that go from the back lower corner to the top front corner. So this is a different triangle. This triangle only has one edge of the cubic unit cell in it. But it's still a right triangle, but only one of the edges are in, only one of the unit cell edges are involved in the triangle. So it's a little bit more complicated. Now, we have to use some geometry. We're going to have to use some Pythagorean theorem. But let's go ahead and relabel these: simple cubic, face-centered cubic, and body-centered cubic unit cells. All right, let's go over here to simple cubic. Let's take a look at the triangle that I want to consider. Here's the triangle that I want to consider. Now, I don't think I actually need a triangle in this case, because remember, the two atoms that touch are right along the edge. What about face-centered? Let's take a look at that. Oops, went up to body-centered, went back to body-centered. Here's the triangle I'm going to consider for body-centered, and for face-centered, here's the triangle that I want to consider. In face-centered cubic unit cells, two of the edges are involved in the triangle. In body-centered cubic unit cells, only one of the edges are involved in the triangle. And in simple cubic, I probably won't need the triangle at all. Let's take a look. What are the radiuses of these atoms? Well, there's one. There's the other one. And so the radius of each of the atoms that are touching falls directly on the edge length. So actually, I don't need the triangle. I know that the edge length equals 2 radii. So in order to figure out what the radii, I can just solve for r, and it looks like it's 1/2 of the edge length. Very straightforward. All right, let's go to face-centered cubic unit cell because that's, I think, the next simplest one. So let's take a look at the radii down here in face-centered cubic unit cell. There's 1, there's 2, there's 3, there's 4 radii. And so what do the 4 radii equal? Now this is where I need that right triangle information. It's a squared plus b squared equals c squared when it comes to right triangles. So there's one side, it's a cubic unit cell length. There's the other side, it's also the cubic unit cell length. So if I take those 2 cubic cell lengths and square each one, then add them up, they should equal the square of the hypotenuse. And the hypotenuse we already decided was 4r, so it's 4r quantity squared. So now it's got a little bit of algebra to do. So on the right side, it's 2l squared. On the left side, it's going to be 16r squared. So 4 times 4 is 16. Now I want to solve. So what do I get? I get r squared equals 1/8 l squared. And then taking the square root of both sides, I get r equals the square root of 1/8 times L. And that's the relationship between the radius and the length of the cell length, the cell edge length in face-centered cubic. Now let's go to body-centered cubic. It's the most complicated. So in body-centered cubic unit cell structures, here are my radii. 1, 2, 3, 4. Now, it is 4 radii that is the hypotenuse, but it's the hypotenuse of a different triangle. One edge of that triangle is, in fact, the length. And so I'm going to end up squaring it. I'll get to that in a second. But this one, this length is different. That length is not the edge length. It's the hypotenuse of yet another triangle. It's the hypotenuse of this triangle. And of course, that's L and L. Well, let's see. So let's go back and let's figure out what this length is. So in terms of right triangles, it's L squared plus L squared equals that length. And so this is what I'm interested in. What is X? What is X squared? So I end up with 2L squared equals X squared. So that's what this length is. And so X equals square root of 2 times L. Now that I know what it is, I can put it back into the formula. So I'm going to go plus square root of 2L. But remember, all of these things are squared. So 4r squared, L squared, square root of 2. Okay, now I got all that. Let's make some room. I know what this is. This one was square root of 2 times L. Now that I know that, I can square it. So let's figure everything out. So I've got, again, 16r squared equals L squared plus 2L squared. Now I got to add it all up. Okay, so what do I get on this side? I get 16r squared equals 3L squared. And now I get r squared equals 3 divided by 16 L squared. And I have to take the square root of both sides. So r equals the square root of 3/16 times L. And so that's the final relationship. And what you really need to be able to do is you need to be able to come up with all these relationships, or at the very least, you have to brute force memorize these formulas for each of these different cubic unit cell structures. That we're going to ask you questions that are going to say, okay, calculate the edge length if I give you the radius, or calculate the radius if I give you the edge length, and I'm going to tell you what kind of crystal structure it is. Okay, that's it.